to present it on the whiteboard? Who would like to do that? Anybody thought about it? Who thought about it? Who did? Okay, great. Well, binoculars also have objective and eyepiece, and I mean, let's try with making it such a way that objective works the same way as in telescope. So let's say that we have objective at this location. And we are looking at an object, a distant object. Somewhere over here. So what does the objective do? It produces an image for the eyepiece. So we need image of the object somewhere here where the eyepiece is. Well, if we have an image over here, what kind of image we are going to get? Real or virtual? On this side of the lens. This is the objective lens. And so now light is coming out from this side. It is refracted, and after refraction it travels here. So, and the image is supposed to be formed here. So the image will be virtual or real? Real. It is formed by the light. Well, definitely the image has to be somewhere along this line. Chief ray is the only ray that when we draw it, we can say, I mean, without knowing the focal length of the objective, we can always say that the image is going to be along the chief ray. So no matter what kind of lens we get, image will be along this line. If we use parallel ray or focal ray, well, we don't know where the focal point is, so we don't know how to draw focal ray, object focal ray. If we start with a parallel ray, we don't know how it is going to be, how light is going to be refracted, because we don't know where the image focal point is. However, chief ray will travel this way, no matter what kind of lens we have. Yes, Eric.
When you adjust the focus on binoculars, is that moving the focal point? Is that what this is?
Yes. Yeah, because eyepiece always works like a magnifying glass, and if you use a magnifying glass, you cannot just arbitrarily put your eye and the magnifying glass. You have to put them in the right place, and actually eyepiece is a pretty strong magnifying glass. You have very little room to maneuver with the object for that eyepiece in order to be able to focus on it, to focus your eye on it. Because eyepiece is supposed to create the image somewhere between your near point and far point. And object for the eyepiece is very close to the focal point, so it is very easy to move image actually beyond infinity, or make an image behind your eyes, or far away. All right. So now let's say when we design binoculars, we have to make it reasonable. So, well, this distance over here is fixed. We don't want to have binoculars which are that long, for example, right? Or even longer. It has to be compact. Well, so let's say that this is the size of binoculars, which means that the image has to be somewhere over here. I mean, not over there. So how about if I mark that the image produced by the objective is here. just for curiosity, let's find out what kind of lens we would need to use. Is it diverging or converging lens? So now, when we already know where we want to have that image, we can select the lens appropriately. What do we have to do? Let's find out the focal points of that lens. So if I draw object parallel ray, it is supposed to be refracted in such a way that it passes through the focal point. Well, I don't know where the focal point is, but I know that it has to pass through the image. Which means that this is the location of the focal point. Which focal point? Image focal point. Very good. This is the image focal point. O stands for objective. Now, how about finding object focal point? Right now, actually, I can do this two ways. I can just measure this distance and mark it there, because focal points are symmetrical. So I can recognize that this is the symmetrical point. Object focal point of the objective is supposed to be here. Or I can construct it also using rays. I know that image parallel ray has to pass through this point. Through the image, right? Now, image parallel ray resulted from refraction of object focal ray. And in order to be refracted in this direction, this is the location where the object focal ray has to hit the lens. And it started from that point. Somehow my drawing is not particularly accurate. Well, maybe not. Maybe not that bad. It's too inaccurate, yeah, but because this point should be symmetrical. All right. So we figured out what kind of lens we need to use for the objective. And if we select this lens, place it at this particular location, the lens from this object will create image over here. Now this image is supposed to be the object for the eyepiece. So how about if I erase these rays? I mean, you won't be able, but so you don't have to erase those. Would be nice if you change the color now. Actually, I could do that too. And now I want to select such a lens that if it uses this object, it produces magnified image over here. And actually, what kind of image it is going to be? Real or virtual? Virtual, correct. Yeah, that light will not go back. All right. So here we have the object. Here we have the virtual image produced by a lens, which we don't know at this moment where to place it, and we don't know what kind of lens we should use. Well, help me. Think where to put it, where to place the eyepiece. And actually, where to place, I have already used this trick at least 2 times in the past. Chief ray is the best ray to identify the location of the element. So I know, and here is the object, over there is the image, So the chief ray is supposed to look like that. Yeah, this is extension of the image chief ray. And this is image chief ray. Where should I place the lens? Where? Where this ray crosses the principal axis, which means that we need to place it here. This is where we need to place the eyepiece. All right, let's now figure out what kind of lens we need to use for the eyepiece. Let's erase this. And well, for that we can use the other ray. So let's use which ray would you like to use, Adam? Which one? Well, focal is difficult because right now I have no clue where the focal points are. Parallel, which parallel? The image parallel ray. Okay, let's use the image parallel ray. Oh, here's the lens. Image parallel ray is parallel to the principal axis. So after the refraction, I should draw a continuous line, and over here it's extension. All right, so here I have image parallel ray. So where is the focal image parallel ray was formed by refraction of which ray? Object focal ray. Correct. Object focal ray. So now, well, object focal ray is supposed to hit the lens at this location. How should I trace object focal ray now? How about if I'll put the ruler, I know that it has to hit here, the lens here. Is this one good? Am I getting closer? Well, what other point, through which other point object focal ray is supposed to pass, or its extension? Yeah, one is here. I don't know where the focal point is, so I cannot. Indeed, I could ask that it has to go through the object focal point, but I don't know where the object focal point is. However, I have a point on the second point on the whiteboard that I know that the object focal ray is supposed to pass through, or its extension. Which one? What is the point? The object itself, right? So the object focal ray is supposed to pass through this point, or its extension. It has to hit the lens at this location, coming out from that side, and either the ray or its extension has to pass the object, which means that the object focal ray looks like this. This is object focal ray. Where's the focal point? Where the ray or its extension crosses the principal axis. So this is focal point of object focal point of the eyepiece. How about we trace now image focal point of the eyepiece. How to do that? Well, I would have now to recognize that in order to get, if I take object parallel ray, well, object parallel ray is going to hit the lens at this point. And it is going to be refracted in such a way that either the ray or its extension will have to pass through the image. And so it will be its extension. Well, so here we have image focal ray of the eyepiece. What lens do we need to use for the eyepiece of binoculars? Converging or diverging? Yeah, light is coming from the left-hand side for both lenses. And so object rays are on the left-hand side of each lens. So for the eyepiece as well, object rays are on the left-hand side on this drawing. However, the object focal point is on the right-hand side, and I think that Oscar knows this because on one of the quizzes I saw that he was pretty good with that. So what kind of lens is this? Which one? You are not sure? Or who is sure? It's a diverging lens, correct. And binoculars, for the eyepiece, in binoculars we have to use a diverging lens. Now, how about focal lengths of the? If we look at the magnification of a telescope, a Keplerian telescope, binoculars are still almost like Keplerian telescope. Magnification is equal to the ratio of focal lengths of the objective and eyepiece. If we now take the focal length of the eyepiece is negative, because this is the case for a diverging lens, I will have a positive number divided by negative number, so quotient is negative, and this minus will give me positive. Magnification of the instrument is going to be positive. And what does it mean? If magnification is positive, it means that how the image is oriented with respect to the object. The same way, correct. All right. I thought also to draw a ray diagram of another type of a telescope, which is also quite common. If you go to a science store, you will probably even find more of that other one than the first one. Now, anybody knows what elements are used in that other telescope which I'm talking about? Mirrors, correct. It uses mirrors. How many mirrors? 2. And how many optical elements altogether? 3, correct. Now name those elements. So there are 2 mirrors and a lens. Where is the lens? Near the eye. So the eyepiece is a lens. All right. So how about if we think about this configuration again and try to draw a ray diagram for a telescope which uses a mirror. A telescope using mirror is called Newtonian telescope. So let's say we have object over here, and instead we don't one mirror, that big mirror which you see inside of that telescope, is really the objective of the telescope. So here we have a mirror. All right, so actually, how about if we now first design approximately how the elements are arranged. Yeah, so here we have a mirror which is at the back. Then where's the second mirror? In front of this one and very close to the eye. Now where do we put the eye? Anybody look through this? Yes. Down, perpendicular to this principal axis, right? So we have another axis perpendicular to this one, and the eyepiece is here. Here we have the eyepiece. All right, so where should we put the other mirror, and what type of the other mirror? Yeah, over here. We should put a mirror over here. And Adam recognized properly that it should be at such an angle, at 45 degrees. Now, what should we, the eyepiece is used, what is the purpose of the eyepiece? It's a magnifying glass, correct. The lights are like a magnifying glass. So in order to see this the image of this object, we need to place the image somewhere in this plane. Right? Now, in order to put image somewhere in this plane, where should be the object for this mirror? Because the object for the eyepiece is an image produced by this flat mirror. This flat mirror produces an image just in front of the eyepiece, on which we look through that magnifying glass, the eyepiece. So where should be the object for this mirror? Over here? Okay, we have a suggestion that it's here. Well, if we place an object here in front of this mirror, we can look at this, just look at the mirror itself, flat mirror, and you put the face over here. So we are looking, where's the image of this point? Where is it? Yes, Eric? Where is the image of this point? Here we have a flat mirror on this side. Very good. Actually, it's true. Vincent recognized that the image is symmetrical about the plane of the mirror. Well, so if I have if this is the object symmetrically if I take now symmetrical, assume that the image is supposed to be symmetrical about the plane of the mirror, it means that the image is going to be here. And we want it to be there, which means that Vincent was wrong. This is not where the image, where the object for that mirror is supposed to be in order to produce the image in front of the eyepiece. Make another try. Try something else. Where we would need the, yes, Andrew? On the other side of the mirror, over here. Yeah, so object for this mirror has to be there. What kind of object it is going to be? Real or virtual? Which one? Virtual, correct. How about this image produced by that mirror? Real or virtual? Real, correct. Light is going to meet here. All right. Now this object, where this object came from? The other mirror created it. This mirror produced image over here. Of what? Of that object. All right. So now we can trace it, right? We have to create image of this object here using this mirror. Help me then. Which ray should I use? Is it smart to use focal ray for this mirror? Chief ray is smart. Why focal ray is wrong? Because we don't know where the focal point is. How about parallel ray? I could trace object parallel ray. But the problem is that I don't know how it is going to be reflected because, again, I need the focal point. However, I can trace chief ray. All right, so chief ray is going to hit the mirror here. And it is going to be reflected symmetrically. Oh, great. So where the image of this point is? I mean, I don't have even to draw the second ray because I know where in what plane I wanted to have the image, and now the chief ray showed me where the image is supposed to be. Where? Adam? Where? Over here? Why? No, it isn't here. Well, we wanted to have image at this location. So image is in this plane, right? Chief ray passes through this point of the plane, which means that the image is here. This is the image formed by the objective mirror. Is the image real or virtual? Okay, I like it, yeah, because somebody says virtual, somebody says real. So we can have a debate. Why is it virtual or why is it real? Actually, it is real. Why is it real? Because this is where the light travels. Right. Now, what kind of mirror do I need to use here? So where is the focal? Now, when I know where the image is, I can find the focal point. So now, let's say if I use the parallel ray, I'm not going to draw. Parallel ray will hit the objective at this point, and that ray will be reflected, or that light will be reflected in such a way that that the ray has to pass through the image. So where is the focal point? Where the ruler crosses the principal axis. So here's the focal point of the mirror. Here we would need to have focal point of the mirror, which means that the mirror is concave or convex? Concave, correct. It's a focusing mirror. Focal length is positive. All right. So we already got the image formed by the objective. This image becomes the object for this mirror. What kind of object, real or virtual? We say virtual, and the reason is because when we place the mirror over here, light will never get there. This line will be an extension of a ray falling on the mirror. All right? So this is going to be a virtual object for this mirror. We have already discussed that a moment ago. All right. So now this mirror is going to produce a symmetrical image, which means that it will create an image over here. I mean, I can actually trace a ray from here. This ray is going to be reflected that way. Now you can recognize now that angle of incidence is equal to angle of reflection. All right. Now, where the eyepiece is supposed to produce the final image? Where? Which lens? This one? I don't think so, because if the final image is on the surface of the lens, it means that you would have to look at that image from this distance, and from this distance you wouldn't see anything. Right? It's too close to your eye. You won't be able to focus on that image. The image has to be somewhere else. Somebody else. Where?
Maybe on the slanted mirror.
On what?
On the slanted mirror.
Why? At least at the yes. So it doesn't matter. I mean, if that telescope is sufficiently wide so that slant mirror is not closer than the distance to the near point, then it's okay. But otherwise, it has to be between near and far point of the eye, and it doesn't matter where. So, let's say then I want to have it here. So, how big is this how big the image is going to be? I know that, I mean, this is the distance greater than distance to near point. How big the image is going to be now? I mean, let's draw the final image. I know that it is supposed to be here. How to find it? Which ray? Which ray? Yeah, let's use a ray to trace it. Pick a ray. Chief ray. Why? Because we don't know where are the focal points of the eyepiece. Let's use chief ray. Well, object chief ray will travel toward the eyepiece that way, right? So now, and pass through the lens this way. So this is going to be image chief ray. So extension of image chief ray is It's going to be like that. So where is the final image? And we know that it has to be somewhere along this line. Well, we already said that we want to have it there. I mean, it's let's be consistent. In this plane. And so the image is in this plane, and image chief ray, extension of image chief ray, hits the plane at that point, which means that here is the final image. Yeah, we see the final image to be much bigger than the, well, actually, no, it's not necessarily bigger, because, I mean, if this one is another planet, well, then this will be diverging and diverging and diverging. However, if I look at the angular magnification, which two angles I would have to compare? The angular magnification relates theta prime and theta. So which angles, where are these two angles? Well, in what angle do we see the image? Where is the eye, by the way? On top. Yeah, over here we put the eye. Yeah, so in what angle do we see the final image? In this angle. And in what angle would we see that star, or star looking directly? Over here. This one? Right, over here. Now we can again recognize that actually this angle, I mean these two triangles, this triangle and this triangle are similar. Now if this object is far, far away, this image is approximately where? At the focal point of this mirror, right? So this distance is approximately equal to the focal length, right? So here I will have, if this is, let's say, h prime, then theta is going to be h prime over focal length of the objective. Now, when we use magnifying glass, we place the object for the magnifying glass almost at the focal point of the magnifying glass. Now, I can recognize that this triangle is similar to this tiny triangle. And I also, since this is a flat mirror, if this size is h prime, this size is also h prime. So angle theta prime is approximately equal to h prime divided by focal length of the eyepiece, which means that if I plug it in here, I did something wrong. Did I do it right? Theta. 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 H prime. I made a mistake somewhere. But where did I do that? Because I should get the same expression for the magnification as I did for a Keplerian telescope. So in order, yes, Jerry. Well, I don't have a problem with negative. Actually, I have a problem here because now, since we are looking at in a completely in a transverse direction, I don't even bother if it is inverted or not. Which one is inverted? Yes, Andrew.
H prime over the focal length of the eyepiece. Where's that H prime exactly?
Here.
So that is the same as the other eyepiece.
Right, because it's a flat mirror here. Right, so these two images are equal. Yeah, because from that I'm getting that this is focal length of eyepiece over focal length of the objective, right? We say? We say? About how, I mean, do you see where I made a mistake? Well, anyway, so find out the mistake then. Because now let's see how we did it for the other telescope. Right, for the other telescope, this was our theta, and this theta was equal to the height of this image divided by focal length of the objective. So it's the same. And theta prime, this was theta prime, was height divided by focal length of the eyepiece. How did we do that? No, this is microscope, the telescope.
Is the theta, if we were just looking straight at the image, so we should draw.
Let's see it.
Well, no, if you were looking at it, like you move the eye around.
H prime. H prime. Ah, no, it's right. Theta prime. Theta, oh, here's where I made the error. Theta prime was H prime divided by focal length of the eyepiece. And angle theta is H prime divided by the focal length of the objective. All right, so now we are home. Okay, so we recovered from that. Now with that orientation, actually, as I said, it is hard to say if it is inverted or not because we are not looking at in the same direction. So in order to make a Newtonian telescope, which is an efficient, what kind of a mirror should we use? What should be the focal length of the mirror? A large focal length, correct. So now, in order to have a mirror with a large focal length, we need, what about curvature of that mirror? Should that curvature be small or large? Large, right? So it should be almost flat mirror. And actually, though, probably you saw on TV the telescopes that, I mean, in observatories, those mirrors have a diameter bigger than a person, and it is almost flat. So the image is produced across a room. A mirror is, for example, here, and the image is produced at the wall. Then at this location over here, we would have a flat mirror and eyepiece on this side to look at the image produced by that mirror over there. Now, how about focal length of the eyepiece? Should be large or small? Small. The smaller focal length, the better. I mean, considering magnification, because there is a limitation imposed by the aberration in the lens, particularly both aberrations, chromatic aberration and spherical aberration. So if we make a lens with a too short focal length, then we will have a problem with aberration. As I was a kid, I was trying actually to use a very short focal length lens to make a telescope, and everything then was in color. I mean, the stars were, the telescope was dispersing the light and produced images in different colors, so I really didn't see the correct image. So this will be all for today then. Thank you very much. Oh, by